Hi, in this video, I'm going to go through the AS-level Chemistry paper from OCR. This is the 2021 paper. It's paper 1, and this is the second half. I did the first half in an earlier video. Okay, so starting off here on this one with question 23. Question about halogens. Chlorine is used to kill bacteria in drinking water. One risk in using chlorine: it is poisonous or toxic. That's fine. That's all you have to say. Okay, chlorine can be prepared by reacting concentrated hydrochloric acid with manganese 4 oxide. Okay, and they've given us they've told us what the oxidation number of manganese is there, which saves us a bit of time. Use oxidation numbers to show which element has been oxidized and which has been reduced in this reaction. Okay, so the first thing to think about here is, right, let's think about the fixed oxidation numbers, hydrogen and oxygen. Okay, now in all of the compounds of hydrogen, it's always +1. Hydrogen's in its compounds there, so it won't have changed at all. Same with oxygen. There's no oxygen as an element there. They're all in the compounds, and so oxygen is always -2, so you can forget about that. So we need to focus on the manganese and the chlorine then. Well, let's have a look at the manganese. Well, as we said there, it's a +4 oxidation state there. Now in MnCl2, the chlorine is going to be a Cl- ion. Okay, so that means the manganese must be an Mn2+ ion. So manganese there is +2. So we can see the oxidation number of manganese has gone down from 4 to 2, so that's been reduced from 4 +4, 2 +2. And let's have a look at the chlorine. Right, so chlorine here must have an oxidation number of -1, because the hydrogen is +1 in HCl, so the chlorine must be -1. Here's chlorine, the element is going to be 0 there. So chlorine has become oxidized then from -1 to 0. Of course, you've got a couple of chlorines there which are still there at -1 still. They haven't been they haven't had their oxidation number changed. They're just spectator ions, but yeah, those ones there in the chlorine, they have become oxidized. Right, so a mixture of perchlorate and aluminium, right, it reacts to form potassium chloride and aluminium oxide, right, a balanced equation. Okay, so we've got KClO4 and aluminium, and the products are going to be aluminium oxide and KCl. Well, we can see we're going to have a bit of a problem here with this, because we've got 3 oxygens there and we've got 4 there. So let's say make that up to 12 oxygens altogether. So we can do 3 times 3 lots of 4 is 12. That means we're going to have 4 lots of 3 there. That's how I would do it. Now we've just got to, right, so that means we've got 3 KCLs. And how many aluminiums? Well, we've got 8 on the right, and so we need to put a big 8 there. Okay, so this is investigating a trend in reactivity of the the halogens, chlorine, bromine, and iodine, and they are dissolved in cyclohexane, which is organic solvent. And we've got aqueous solutions of the halides: sodium chloride, sodium bromide, sodium iodide. We're going to plan an experiment on a test tube scale that would show the trend in the reactivity of the halogens. Okay, so we're going to do this by looking at displacement reactions. Okay, now I think the easiest way to do this is probably draw it as a table. And let's think about the, the observations. All of these solutions of aqueous halides, these are all colorless. Don't forget that. People always think for some reason sodium bromide is red. It's not. It's like sodium chloride, salt, it's not green like chlorine, it's colorless in solution. Same with sodium bromide and sodium iodide. Okay, so what's going to happen when we do these reactions? Okay, so let's get rid of that. We're going to mix the the halide with a halogen. Okay. Now we're going to shake it. Right, now cyclohexane will not mix with water. So you're going to, and the cyclohexane is less dense, that will float on the top. Okay, so this is always going to be colorless, this bottom half. And then the top half can be different colors. If you've got chlorine in there, it's going to be pale green. If it's bromine, it's going to be pale. It's going to be orange, and if it's iodine, it's going to be violet. Okay, so you can tell which the halogens there. That's what we're going to do. So let's draw a table. And right, so I'm going to do it here, give myself a bit of room. Right, so we're going to have here on this table, I'm going to have the halide, the aqueous halide. So here we've got KCl. Let's say KCl or NaCl, it doesn't really matter. It says NaCl. Yeah, let's put that down. NaCl, NaBr, and NaI. And then we're going to add to those the halogen in our cyclohexane. Right, so we're going to have chlorine, that's going to be pale green, and put that in cyclohexane. We're going to have bromine and iodine. Now, with this, so we're going to get two layers, as I said. The bottom layer is always going to be colorless. So the observation we're looking at is we're looking for the color of the cyclohexane layer. That's the see if there's any color change there. Right, so obviously we're not going to react the halogens with themselves, so we can put across there sodium bromide with bromine and sodium iodide there. Right, let's do this sodium iodide and chlorine there. What's going to happen there is the cyclohexane will turn violet. And the reason for that is because chlorine is more reactive than iodine. Yeah. And so the chlorine is going to displace the iodine. You're going to get sodium chloride. I'll just write it down there. So you're going to get sodium iodide. It doesn't ask for it wants an ionic equation. I'll just write this now. And it's going to give you sodium chloride. And the iodine is going to make the thing purple. Right, it does ask for an ionic equation for them. So let's write the ionic version of that. So that's just going to be 2I minus. We get rid of the sodium ions, the spectator ions. They don't do anything. They're just Na pluses. Floating around doing nothing. We're going to get 2 chloride ions and we're going to get iodine. So it will turn violet. That's the observation there. So the cyclohexane will turn violet. It will go from green, pale green for the chlorine, to violet. Let's see what happens here with this one. Okay. This box here. Chlorine to sodium bromide. The chlorine will displace the bromine. It's more reactive. So it will turn, the cyclohexane will turn orange. Right, let's do this box here. What's going to happen here? Bromine is added to sodium iodide. Bromine is more reactive than iodine. So the violet hexane, the orange hexane layer will turn violet. Bromine to sodium chloride, no visible change. I just wrote NVC, no visible change. The chlorine and the cyclohexane will stay green. Iodine to sodium chloride, no visible change there. Either there'll be no reaction because iodine is less reactive than chlorine. Iodine added to sodium bromide, the last one, no visible change there because iodine is less reactive than bromine. So just to state the order of reactivity, the most reactive at the top, you're going to have chlorine, then bromine, and then iodine. Okay, that's what we need to do for that question. That's 5 marks for that question. Right, now we're on to organic chemistry. Right, we've got outline the reaction mechanism for reaction 1. Okay, so methyl propene is reacts with something. So it tells us surely that it reacts with hydrogen bromide. It does, but I've missed that bit of the question out. Reacts with HBr. Okay, so we've got to draw the mechanism for that. And what's the name of this mechanism? Well, it's called, or let's down first, it's electrophilic addition. Right, let's write down the mechanism then. Okay, so we get HBr. We want all dipoles on this, so we're going to have a delta positive on the hydrogen, because the bromine is, that's going to be delta negative. Bromine is more electronegative than hydrogen. The first step in the mechanism is for the pair of electrons in the pi bond to move onto the hydrogen, and the pair of electrons in the hydrogen bromine bond, that breaks and they both go to the bromine. Okay, that is going to give us the following intermediate. Right, so that's now a single bond. The new hydrogen has stuck onto that carbon there. Okay, and that means that we have got a positive charge on this carbon. This is this intermediate is a carbocation, right? And we've got Br minus here. And the final step in the mechanism we want to draw is for one of the lone pairs of the bromine to move onto the carbon with the positive charge, and that will give us our product. Okay. Okay. Okay, that's everything that you need there. Okay, when reacting methyl propene with HBr, a small amount of compound B also forms. Compound B is a structural isomer of A. What is a structural isomer? Well, the definition of a structural isomer is same molecular formula, but different structural formula. All right, now the next question is going to ask us, what is that show the structure of compound B? Well, let's have a look here. Okay. Well, compound B results from the following happening. Instead of the hydrogen sticking on, so if I just rub this bit out here, instead of the hydrogen sticking on that one, the hydrogen first of all sticks onto the other one. And that means you're going to have that as a carbocation. So that means the bromide ion is then going to react with that carbon there. So you get the bromine, it gives you, the bromine goes on the end carbon atom instead of the middle carbon atom. Compound A can be refluxed with a reagent to make alcohol C. Okay, choose a reagent and complete the equation. Okay, so in order to swap that Br for an OH, yeah, all right, that's what, so the compound, the alcohol is going to look like this. Okay, that's going to be the alcohol. Make sure your bond is going to the oxygen there, not to the hydrogen, or we'll knock a mark off. Okay, so that's the alcohol. Now that is nuclear. What reagent are we going to need for this? Well, it's nucleophilic substitution. So we want OH minus, yeah. And that, of course, is going to attack this carbon here because you've got delta positive on it. But what's the reagent? It's not. You can't just say OH minus. You have to say sodium hydroxide, and it's important that it's in aqueous solution as well. Right, and what's the other product made here? Well, the sodium and the sodium ion, spectator ion, those are the bromide ion forms, so NaBr. Okay, draw a label diagram to show how to separate the apparatus for reflux. There's 2 marks there. So what we want to do, reflux, you have a flask, pear-shaped flask or round bottom flask, doesn't really matter. And on top of that, you're going to have, connected to that, you're going to have a condenser in the vertical position. Okay, so we need to label the flask. This is the condenser. I want to say the water should go into the bottom, the water in there, and the water out coming at the top. It's only 2 marks. You might not actually even have to label the water in, the water out, just the condenser and the flask. Okay, this question is about the analysis of unknown compounds. Scandium, atomic number 21, reacts with oxygen to form an oxide of scandium. Student carries out the experiment. Okay, so what is he going to do? He's going to get a crucible in a pipe clay triangle. That's just to hold it on the tripod. He's going to heat it up. He's going to put his scandium in here. Okay, he's going to heat it. The scandium is going to react with oxygen to form an oxide of scandium, scandium oxide. We don't know the formula of it. That's why I write the name and not the formula. Scandium oxide. And of course, this is going to be heavier than the original scandium. And the extra mass is due to the fact that it's got oxygen in it. So we can find out the mass of scandium, find out the mass of oxygen, find out the moles of those, and work out the ratio of those moles to work out the empirical formulae. And that's what we're going to have to do. Okay, so student results, determine empirical formulae. Okay, so the empty crucible weighs this much, 12.165 grams. So we're going to subtract that from the others. Okay, so if we, so this one here, okay, the mass of the crucible in the scandium is equal to that. So the mass of scandium is going to be 12.435 minus 12.165, which gives us 0.270 grams. Whereas the mass of the crucible and the scandium oxide, right? So the mass of the scandium oxide, again, I don't know the formula, so I'll just write it like that, is going to be 12.579 minus 12.165, and that is equal to 0.414 grams. Okay, so we need to work out the mass of oxygen now. So we know the mass of scandium, that's 0.270 grams. We need the mass of oxygen. So how are we going to do that? Well, the mass of oxygen is going to be equal to the mass of the scandium oxide minus the mass of the scandium. So that's 0.414 minus 0.270. So that gives us 0.144 grams. Okay, so now we need to work, we've got the masses, we need to work out the moles of each, right? So let's do the moles of scandium. That's going to be equal to the mass over the AR, the atomic mass of scandium, which is 45. So that's 0.27 over 45. That gives us 6 times 10 to the 26 times to the minus 3 exactly. Right, let's do the mass of oxygen, moles of oxygen. That's going to be the mass over the AR of oxygen, 16. So the mass is going to be 0.144 over 16, which is 9 times 10 to the minus 3. So we can see the ratio then, mole ratio of scandium to oxygen is 6 times 10 to the minus 3 to 9 times 10 to the minus 3. Now you can probably see that that is already, that's a 2 to 3 ratio. The normal thing we do is divide by the smallest number. The smallest number is 6 times 10 to the minus 3. So divide by that, you're going to get 1. You get a 1, 9 divided by 6 times, that gives you 1.5. Right, that's not the simplest ratio, so we have to times that by 2. That gives us a 2 to 3 ratio. So the formula of our scandium oxide is SC2O3, which is what you would expect because scandium always forms a 3+ ion, you may remember. That's the first transition metal in the row after calcium. Right, anyway, that's the formula Sc2O3. Right, the student was unsure all of the scandium had reacted. Suggest one modification that the student could do to make sure, to be confident that it had all reacted. So what you should do is you get your crucible with your scandium oxide in there, okay? And you will weigh it. Then you should heat again. And then weigh it again. Now, if the mass hasn't changed, we'll call that heating to constant mass. It will mean that the scandium is all reacted. But if it gets heavy, if it gets a little bit heavy, it means that not all of the scandium had reacted the first time you heated it. The second time it took in a bit more oxygen. And so you just keep on doing that, repeat the heating until the mass doesn't change, and then you can be fairly sure that all of the scandium has reacted. And that's a fairly standard question. Heating to constant mass is a fairly well known technique. Okay, right, this is going to be the ideal gas equation. Okay, a gas cylinder has a volume of gas. It gives you the mass of the gas in there. And we've got to use this information to determine the molar mass and the possible. How are we going to do that? Well, we're going to use two equations, aren't we? We're going to use PV, the ideal gas equation is nRT, where n is the number of moles. And we also have the n, the number of moles, is equal to mass divided by the molar mass. I'll call it MR. So let's substitute the value of n into that. So that gives us PV is equal to mass RT over MR. Well, we're interested in finding out the MR. So we rearrange that equation. That gives us MR is equal to mass RT over PV. Now, when we're doing the ideal gas equation, we've got to be careful with the units. Right, now T is in kelvins, okay? We've got 20 degrees C, so what's that in Kelvin? We add 273, that's equal to 293 Kelvin. And the volume, we've got to be careful of. So let's say the pressure has got to be in pascals. That's already in pascals, so we don't need to worry about that. But the volume there, they're giving us in dm cubed. It should be in meters cubed, okay? Right, now there are 1000 dm cubed in 1 meter cubed. People always get confused with that. And don't forget, there's also 1,000,000 centimeters cubed in a meter cubed. We don't need that, but it's just worthwhile mentioning it. Okay, so what's 9.3 dm cubed? I've got to divide by 1,000 to give me in meters cubed, so that's going to be 9.39 times 10 to the minus 3. Let's put those numbers into the equation there. The mass, they tell us, is that in kilograms. Now we need to convert that to grams, of course. So times by 1,000, that's 1690. The ideal gas constant in our data book is 8.31 joules per mole Kelvin. Temperature is 293. Divided by the pressure, they tell us, is 1.37 times 10 to the minus, plus 7. Okay, and the volume is 9.39 times 10 to the minus 3. If you put all of that into a calculator, you will get the answer. I get the answer to be 31.98. Okay, now that is pretty close to 32. What well-known gas has a molar mass of 32? Well, the one I'm thinking of is oxygen. Okay, O2. Okay, here's the last question on the paper. Right, we've got a compound E. It contains carbon, hydrogen, and oxygen only. And the mass and infrared spectrum of compound E are shown below. Right, so what we need to do here is let's look at that there. Okay, you can see that the parent ion there, that is 88. Mz is equal to 88. So that means the molar mass of this compound is got to be 88. There's also another little bit of information there is that might, I don't think the mark scheme doesn't need you to rely on it, but you can see you get a very common fragment there of MZ43. So that might help us a little bit as well when we're trying to work out what the structure of E is. Okay, the important thing is the MR is 88. All right, let's look at the infrared spectra now. Okay, infrared spectra, of course, all of this stuff here is the fingerprint region, so that doesn't really help us, doesn't tell us much. This peak here is very characteristic of a carbonyl. Okay, you can tell it's a carbonyl really by looking at the shape of it and the approximate position rather than looking at the exact position, because look, 1630 to 1820, well, there, that is on 16, that's about just over 1700, right? It's in the right place, but it's also quite fairly broad and quite deep, and that's very characteristic of a carbonyl. One though, and you have to be careful, don't, if you alkene, the CC bond here, right, that is in it, that's in a similar range, that alkene there, 1620 to 1680, so it's a little bit to the right of that peak, but not much. But I think the way you can spot it is it's much narrower and it's less deep. It's always like looks more like that. Okay, in that position. So we've definitely got a carbonyl there, and that fits in with the fact that C, it's got oxygen in the molecule. It tells us. Now the other thing that is extremely characteristic here is this peak here. Now, without even looking at the numbers, you can tell that is down to an OH from a carboxylic acid. This very broad peak is very characteristic of that. There we go, in that range there. If you want to distinguish that from an alcohol OH, I'll just rub that out for a minute. That's quite useful to point that out. And alcohol OH is ever so slightly, it's a little bit to the left of that, and it's a bit narrower as well. So you tend to, alcohol peak, you tend to get like that. And then you get this, that second peak there. See that there? That is due to carbon-hydrogen bonds, which are of course present in every organic compound. So it's not very useful to know that. It just helps you spot the alcohol one because it's got that double thing in it. Okay, so we've got an OH. What do we know? Let's the summary. What do we know about this thing then? We know we have got we've got an MR. The molar mass is 88, and we know we've got a carboxylic acid group in there as well. Okay, and it said it could be two different things. Well, let's just see. Let's think a carboxylic, it's obviously not going to be a methanoic acid. That's going to be the MR is going to be way too small, isn't it, for that? But if I put an H there, it's not going to be methanoic acid. If I make it ethanoic acid, change that to CH3, the MR of that, if you work that out, that's equal to 60. So it's still some way off 88. If we stick another CH2 in there, CH3, make it propanoic acid. Well, that is going to be add 14 to 60, 14 for the CH2. That's going to be 72. It's still not enough. Okay. Hang on a minute. Okay, so if we have butanoic acid, that is 88. Okay. So let's get rid of that. That has got an MR of 88 butanoic acid. Now it said it can be two different things. So, well, what could we do there? We could just put a branch in that chain. So let's have a methyl group there. Okay, so it could be either butanoic acid on the left or methyl propanoic acid on the right. And then that extra bit, remember I said about the fragment which has got an MZ of 43. So it can produce a fragment there. Well, that fragment there, the propyl fragment, that weighs, if you add that up, that weighs 43. And you've also got that there. This is, that's also 43. So that fragment is consistent with both of those compounds there. Okay, that is the end of the paper.